Okay, I'm using a little bit different video format this time for the remaining problems so that I can record a little bit longer videos and I don't have to break them up so much. If anyone notices any trouble with this, please let me know. We left off on number 22. So number 22, we have, let me just get my draw up here. Right here. Okay, so we have a minus b over so we have a minus b over b minus a, and we want to know whether or not that is equal to -1. I have here a relation of a minus b over a minus b, and we know that that is equal to 1. And we know that -1 can either be equal to -1 over 1, or 1 over -1, or -1 times 1. So knowing these two things, we can say that -1 is equal to a minus b over a minus b. That is equal to, right here, a minus b over a minus b times 1 over -1, right? Here I just have, I substitute instead of 1 here, I have a minus b over a minus b. I know that -1 can be equal to 1 over -1, right? And then if I multiply these two fractions together, I have a minus b over a minus b times -1. This is equal to a shift in the signs, right? So -1 times a is -a, and -1 times -b is positive b, right? Then we can switch the order that we write these to, and we have a minus b over b minus a, and that is indeed equal to -1. Generally, we use the little shortcut method in our head. We are doing all of this, but we can write it as a minus b over b minus a, and we factor out -1. That's usually what we say there. And that way we can switch the order of the signs and still have something that is equal. So that's number 22. Number 23, we want to know if negative a plus b is equal to negative a plus b, and it is not. One thing that we can do is just evaluate the left-hand side, and we get this negative, right, which is actually the same thing as -1 times that quantity. We can then distribute the -1 to both a and b, and we get -a minus b, and that is not equal to -a plus b. So that's number 23. Number 24, we have a to the r to the power of 2, and then if we have a power raised to a power, we multiply the two powers together. So we have a to the 2r. And of course that is not equal to a to the r squared. Alright, so for number 25, we have the quantity of a squared plus 1 to a 1/2, and of course that is not equal to a plus 1. To see this, we can think of the quantity of a squared plus 1 to a 1/2, raise it to a power of 2, right? So power raised to a power, this would become 1, and that's equal to a squared plus 1. Do the same thing on the other side, right? Square a plus 1, and if you do that, you get a squared plus 2a plus 1, right? So there's this missing term of 2a between these two things. We squared the left-hand side, and we squared the right-hand side, and if we do that, we did the same operation, so the two things that we get out should be equal, but they're not, because there's this extra factor of 2a there. Number 26 is a little tricky, right? We have r over s plus s over r divided by the quantity of r squared over s squared minus s squared over r squared. First thing that I did was combine the lower fraction, right, into 1. So we have, in the denominator, we would have r squared s squared, In the numerator, we would have, here we're, and essentially what that is we're just multiplying r squared on the top and bottom of the first fraction, and s squared on the top and bottom of the second fraction, so that we have a common denominator, right? And then this becomes s to the fourth and r to the fourth, and so it would be r to the fourth minus s to the fourth over r squared, s squared. And that would all be one fraction. And then if you divide by a fraction, you multiply by its reciprocal. And that's what we have here. Right? So this is the reciprocal of what we found in the denominator. So you do the same thing with the numerator, combine the fraction. Right? You don't have to find the reciprocal because it's already in the numerator. And when you multiply that together, you get some cancellation, and r and then s in the denominator is equal to, or is cancels with an r and the s of the numerator of the second factor. And then you have this, right? When you simplify that out, you have rs times the quantity of r squared plus s squared divided by the quantity of r to the fourth minus s to the fourth. So this is pretty good, right? If you get to here, you're at the pretty good level. But there is still some factorization that you can do and some simplification that you can do. So one thing that you could do is recognize the fact that r to the fourth minus s to the fourth can actually be written as the difference of perfect squares, right? Where r to the fourth is equal to r squared squared, and s to the fourth is equal to s squared squared. So that can be factored out into, right? So it's the same thing as, let me write it right over here, right? If I have x squared minus y squared, it's equal to x squared, or x plus y times x minus y, right? So if I have x squared squared and y squared squared, then I would just raise each one of these to a power of 2. And it's the same idea. So you can factor that out again, and lo and behold, you have one of these on the top and one of these on the bottom, and therefore they cancel. So then you have rs over the quantity of r squared minus s squared. And that's acceptable. That's very good. The really above and beyond, right, is to maybe even simplify that a little bit more, where you have, this is the combination of factors. It's the same thing as what we found up here, right? Only instead of a plus term, you have a minus term, right? So you might represent it this way. There's some rules for simplification that I follow. The first one is, can I qualify the domain easily? Can I understand what numbers don't give me division by 0 easily? And if I use the expression later, it will be easy to recognize factors that I can cancel. So if I use my simplified expression and I substitute that somewhere else, will I easily see cancellations, right? With this expression, I might not easily see a cancellation as well as I could if I had substituted this instead. So, and then if you can get to this, if you do this, or this, really, that's what I call Yoda level, right? And that's my little picture for that. That's all I've got. We'll start at 27 in another video.